So record, screen share of my iPad. Here we go. Oh, I should probably plug in my iPad. That means then. Ooh. Okay. Okay. So I want to just kind of talk through a little bit of the things, come on, that we were talking about before, right before school closed, and then going over what we've talked about so far, because a decent amount of these topics feel like I'm kind of just doing the same thing over and over again, and I want to be sure that there is a little bit of a distinction so that way it doesn't all just mush into one thing in your brains. That's a thing of your historical peers as well. That's not just like oh no, this year, this class because of remote learning. These topics are really similar, but they're a little bit different on purpose, and they have serve a slightly different purpose. So I wanted to make sure that that part was clear. So before school closed, actually even literally the Friday while school was like technically announced closed, but my 6 block was nice enough to actually still show up to school, we talked about this idea of a normal curve and that 68, 95, 99.7 rule. And what this tells us is that if you have a population that is already in a normal distribution, it's going to look like that beautiful normal curve. And then we can lay out these percentages. And when we do, then we can say like, oh, the data of the population, 68% of it lies within 1 standard deviation, 95 within 2, and so on and so forth. I guess one thing I'd want to put down here at the bottom is that this is like mu plus sigma, and this one's like mu minus sigma, and so on, moving outwards. And then that's the way like a normal curve and normal distribution gets laid out. That was only the case of if we were talking about a population that was already normal. If it wasn't normal, we could do no things. We love normal populations, but for right now, we were just saying like, unless the population is normal, I'm doing nothing. If it is normal, here's the information that I get to know. Then right at the beginning of remote learning, we did that week where we had the simulation and we said, okay, start with a normal population, do this idea of sampling distribution of means, which says take a bunch of samples and then average them. And when we do that process over and over and over again, what we learned is that that sampling distribution of means, this thing turns out to be always normal. Oops. Always normal. And the reason that that was cool is because now, even if the population wasn't already a normal curve, we could do this process of take a bunch of samples, average them, take a bunch of samples, average them over and over and over again, create that sampling distribution of means, and now we always have a normal curve, which is great because then we can say things about that 68, 95, 99.7 rule. So regardless of the population. So what's good about that is that means like, okay, great. So now we always have a normal curve. So we can always get a sampling distribution of means that looks like this. However, the one difference here and the thing that came from the central limit theorem was that, yes, it's still talking about that 68, 95, 99.7 rule. Yes, I am still saying that I'm centered at that population mean because that's the way that things work out. However, this time, when I go 1 standard deviation away, that distance that I'm going, I don't want to go a population standard deviation away because this is much narrower than the population. So what I mean is that now we have to go that mu plus sigma divided by root n, because that's our new, what we found to be the convention of what is a good distance away to be that new standard deviation. It is kind of approximating a sample standard deviation, essentially. So we can go that distance away. So mu plus that sigma divided by root n, and mu minus sigma divided by root n. And now we can say, okay, great, in the same way that we did before, this is 68%. However, this is no longer talking about 68% of the population data. This is saying 68% of averages of samplings. it's talking about where the averages lie. And that's the reason that it got so narrow, is because yes, it's possible that you had a population data value that was way, 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 way big, and that would make your overall population spread very, very wide. However, when I grab 17 random samples, it's really, 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 really unlikely that I'm gonna grab all 17 that are gigantic, and in the end then have an average that's gigantic. When I grab a bunch, I'm going to grab them from all over the spread of that population, and the averages that I get when I take the average of those data points is going to be a much smaller number, which narrows in that population. So now I'm talking about when I have this sampling distribution of means, I'm no longer saying 68% of the data. I'm saying 68% of those averages, where you grabbed a bunch, took an average, 68% of those numbers lie within that one standard deviation. Okay, so that's part 2. And then we continued on moving into part 3. And part 3 is the thing that we just talked about. Hang on, let me just check the chat, make sure this isn't a question. In case any of you are unable to stay on for the whole time, I just want to double check. I'm recording this right now. I will put both this slide and the video of it on your assignment when this is over. So especially if there's someone else who is your buddy who's currently sleeping through class, it'll be on there afterwards. So I just want to make that part clear. Okay, so then the last thing. We talked about sampling distribution of means. We found out all the percentages that existed there. And then after that part, we just recently learned about this new topic that is confidence intervals. And the reason we talk about confidence intervals at all, the reason we want to know this is because we study populations that are too big. And when I say too big, what I mean by that isn't like, oh, lower your scope. You can't know about all men in the United States. Like, no, what I'm saying by too big is that they're too big to know everything about, like to actually ask them all. I'll say poll them. They're too big to actually poll. And therefore, we're going to have to do things where we make guesses about things about the population because we don't even get a whole set of population data to begin with. So now instead of saying like, okay, I've got the whole population, I'm going to do some stuff and create some normal curves, and now I can say things about percentages of averages. Now I'm saying I don't even know anything about the population to be able to grab all those random samples. So rather than saying like, go from this population data that already exists, you're going out into the world and you're the one getting that population data. And what I mean by that is you go out and you sample a bunch of people and you take those averages. So you still do that process of sampling distribution of means, of sample a bunch and then average, because that's what gives us the normal curve. So you still do that whole process because that's what creates the normal curve for us. And that's an important thing to do. However, this time it's not necessarily this beautiful picture where I'm like, ah, yes, I know the population is a uniform distribution and it's a little bit skewed this way or whatever else I'm trying to say. I don't think uniform can be skewed, but I know nothing about the way the population looks. I'm trying to do this process to estimate things about the population. So what I'm going to do is I'm going to get to this point. I'm going to get to this point and I'm going to realize like, okay, great, I did all of these samplings and here's what I found out. I got to a place and in the end we get a sample mean or an average. And that's what the one that we call that X bar. Now from there I can say, okay, great, if my X bar is this value, and I think that things exist in the way that a normal curve does, like up here, that means that my X bar falls into one of the values all in and around here. I don't know where it is, but my X bar hopefully fits somewhere on my normal curve. I'm gonna do all of those, but my X bar hopefully fits somewhere within that space and within that realm, so then I can say things. And then it's up to me or whoever I'm studying or whoever is in charge of the study that I'm performing to decide, well, how sure do I want to be about where that X bar is? And how much do I really want to say about what's going on? And the reason that I do want to know things about that is, do I want to say that like, okay, I'm pretty confident that this X bar is within that first standard deviation away, and therefore I can like really close in and tighten in to say like, oh, I think the population really is there? Or do I want to give myself a little bit more leeway and be more sure that I'm actually capturing the population mean? And the reason that we do that is then just how many standard deviations away? How close, how far do you want to be from that mean? How sure do you want to be that you're capturing it, but at the same time, still saying something important? And the reason that I say that is a lot of times if you go out and say like, I want to do a 99.7% confidence interval, yeah, like you're going to end up saying something like, well, it's between 0 and 100% of people, or something really close. It's between 1 and 99% of people that think this. And it almost becomes like not interesting to say anything at all, because you're so sure, so you widen your range so much that you're no longer saying anything. However, the other side of that, you're like, well, then squeeze that interval, make it really like small. Why not? If I try to go so far in and I'm like, oh, it's between 51 and 53% of people, but I'm only about 10% sure, it becomes too close of an interval and not with enough percent believability that it even makes sense to talk about. So we kind of usually stick with this like between that 68 and that 95 range, because that gives us a tight enough interval that it's still saying something novel, but at the same time, it's like a high enough percentage of confidence that you're actually capturing the population mean that it means something to someone when you say it. Because if you say, I'm 5% sure that it's between here and here, everyone's like, great, I don't care about your 5% sureness. So the way that this works is you say, okay, I want to be, I don't know, 95% confident in the guesses that I'm making, which means that that sample mean that you found needs to be within that range of that 2 standard deviations. It needs to be within this space right here of that population mean. However, that secret game that we were playing, and when Mr. Henke did the video, he said, like, let's play this weird hypothetical game. That secret game that we're playing, it says, well, do I know, is my X bar there? Possibly, or is my X bar there? Possibly, and I have to consider those as like 2 separate situations. So we have to consider both. So we have to say like, well, what if X bar is bigger than the mean, than the population mean? Then we'll have, I'm just going to continue to use the picture because it's much nicer than my drawings. Then we'll have a situation like this where, okay, my X bar is this value way out here. And I'm going to have to say, okay, do X bar and then subtract off 2 of those edited standard deviations in order to get my bottom guess of what mu might be in this case. That's how I'm guessing it. But I can also say, if that X bar is less than mu, it's possible that I'm talking about this side, that my X bar, that the sample mean that I found was smaller than my population mean. Then I can say, okay, great, here's my normal curve. I think that my sample is right here at this spot, at this X bar. So that means that my, the color I've been used, that my mu is up here and is going to be much bigger. So in order to find that mu, I should do, well, take my sample mean and add on those 2 modified standard deviations. And that's why we have that adding and subtracting, and where we get that weird image from in the end is because we get an image, whatever, I'll just draw it out really quickly. We get an image that looks like this, where the overlap is actually your X bar, but essentially this image becomes that picture and this image becomes that picture, and you saw the wonderful visual of that because of technology that Mr. Henke slid the 2 normal curves on top of each other there. But then this can tell us, oh, that means that the interval that I want to use to describe where the population mean might be lies from whatever that orange value is to wherever that blue value is. And that's the interval that I'm picking. Because it's possible that from up above, the sample that I found was way out here and way bigger, but it's also possible that the sample mean that I found was way out there and way smaller. So we're covering all of our bases, and we go that number of standard deviations away. That's what the confidence interval formula is doing, rather than just like plugging in the values of what's going on there. Okay, so with all of that in mind, I'm going to give you like a minute to digest that while I stop sharing and recording, and then we move on to NBA weights. But before I do that part, do you have any questions or clarifications about any of the stuff that I was just talking about? Moving from before school closures all the way through what we've been doing as far as normal curves, confidence intervals, all that stuff. Okay, I'm going to stop sharing and stop